And that was a joke, not to be taken seriously, that somehow a creator was doing this. That was not the view I held at all. This is a joke.
What happens when a Nobel Prize-winning scientist replies to his intelligent design critic? That's what we're going to find out today. Specifically, Stephen Meyer, a leading intelligent design guru, has taken aim at Roger Penrose's conformal cyclic cosmology. So who better to reply than Roger Penrose himself? We'll also hear from another scientist who's worked on a version of CCC, Niayesh Afshordi, who's my co-author on the book The Battle of the Big Bang, which explores competing models to push beyond the Big Bang. And do stick around until the end, as Penrose reveals how he is so often misquoted when it comes to the issue of fine-tuning.
It's not chosen randomly out of the possible, all the possible universes. It's just telling you that's wrong.
But first, let's see how Meyer misunderstands the Penrose-Hawking singularity theorem that is so often used to prove a beginning of time.
Penrose and Hawking and another collaborator, later George Ellis, solve Einstein's field equations, and they do so not making some simplifying assumptions that Lemaitre had made, but eliminating those simplifying assumptions and solving them with full rigor, thus showing that the implications of Einstein's theory are very definitely that the universe had a beginning, not only in time, but also in space, that there's a point where the curvature of space gets infinitely tight, corresponding to zero spatial volume. Now, you have to actually, that's a profound image, because if you think, how much space can you put in, how much stuff can you put in zero space? The answer is obviously none. And so the singularity theorems have a kind of profoundly anti-materialistic implication, because they suggest, as Hawking and Ellis later put it, that this looks something like a creation event.
The singularity theorems told you that the physics that we had at the time isn't adequate to describe what happens the theory tells you that classical physics runs into singularities. It doesn't tell you what happens. Does a different kind of physics come in at those singularities? Maybe so. It just says that the physics of the time isn't adequate to tell you further what happens at the singularities. That's all it is. You might have a better theory. You might have a theory of quantum gravity, which says, okay, no, this is what happens earlier. But current theory would not give you any picture of what happened before the Big Bang. Now, when I say current theory, that was then. When I say current theory now, I mean my view now. My view is very different. My view is that the Big Bang was something that you can explain by conformal geometry. In conformal geometry, the Big Bang was nice and smooth, and it joined onto something else nice and smooth, which was the remote future of a previous cosmological eon. There were various little points on it where things really do go bad, and those little points are what we call Hawking points. And those are where all the entropy goes. So the entropy goes up, and they get swallowed up in the Hawking points. But the rest of the universe is nice and low entropy and ready for another start. In this scheme, the universe didn't come from nothing. It came from something. And you can even explore what that something was.
What that something was, in Penrose's view, is a cyclic model. And that's what Meyer is now attacking. But can he even get the name of the model he criticizes correct?
The Penrose cyclic conformal cosmology model is its formal name, the CCC.
It's not quite right. It's conformal cyclic cosmology. They both begin with C, don't they?
Now, that's not too bad. We all make mistakes. But what's worse is when Meyer describes how CCC actually works. Now, if you want to know more on the model, do check out our longer video on the topic. Links in the description below. But a brief summary of CCC is that it says that with no mass in the early or late universe, there's no way to build a ruler or a clock. So there's no scale, and big and small become equivalent. Switching to this scale-free or conformal geometry removes the singularity, and according to Penrose, implies a series of cyclic eons where the universe forgets how big it is. In a related periodic time cosmology developed by Afshordi and Gould, the same thing happens, but the future and the past are glued to each other to form a loop. Both use conformal rescaling, and it's this that our intelligent design guru Meyer seems not to understand.
An endless series of expansions, and then out of little patches as I can, as best understand the papers.
Okay.
These guys are not real vivid in their visual descriptions of what they're modeling. But
now that is a bit ironic because Penrose is famous for his visual descriptions.
The sense you get is that you have an expansion, and then there's out of somewhere in that existing universe, there's a patch of that universe.
That's just plain wrong. The next eon just describes the whole universe, and it comes from the whole universe previously. There's no little patch anywhere in it. That's not part of the story.
Maybe he kind of watched this video that we had, that there is a little patch that comes up, because that's the only reference to a little patch that I know of. And of course, our video is just, I think, an animation. We shouldn't take it too seriously in that sense, because really the entire universe maps to the entire universe. In all versions of CCC, it's the entire universe that maps to the entire universe. It's just that it loses a sense of a scale, or is this what Roger calls conformal rescaling, because the theory becomes scale-free at some point in the far future and near the Big Bang.
There's a patch of that universe, and out of that, then there's a new field that's activated, which he calls a phantom field.
Okay.
And for the phantom field to do work, it's got to overcome the entropy that's been built up, the disorder that's been built up of the first cycle of expansion. And so what Penrose does is he attributes to the phantom field properties that are associated with no known physical field.
Forget the phantom field. There's nothing in the description. Probably did use the term phantom field at one stage, but it doesn't feature in the modern scheme. I should say that I wrote a book called Cycles of Time, and people ask me, they say, should I read it now that maybe it's all out of date now? And I say, read the book, fine, but don't read any of the appendices. The appendices have to be rewritten. And I suspect that the term phantom field, I've forgotten. If it appears in my writings, it probably appears in those appendices. I don't know. I've forgotten what it means. That's not the term that I would use now. There's no such thing as a phantom field in the scheme.
Now, it's true there was a reference to a phantom field in some of Roger's early work, and maybe that wasn't the best choice of words, but when you understand how CCC actually works and what a phantom field is, you'll see that they're not really related. So, what is a phantom field?
The idea is that basically you don't necessarily have negative energy densities, but if someone starts moving with very fast speed, then you could see negative energies. Technically, this is called violation of null energy condition. In the standard model of CCC that Roger promotes, and the ones that others, like, for example, in our version, we adopt, you don't really need a phantom field. The idea is that universe becomes scale-free, so you have to think about what relativists call a conformal time. And within a finite conformal time, universe becomes really big. Even with the standard cosmological constant, there is no need to exotic phantom field.
One of the main motivations for CCC is to explain the mystery of the low entropy at the Big Bang. Again, for more details, see our longer CCC film. But the basic summary is that black hole evaporation and conformal rescaling kills off the entropy of the previous cycle. It's got nothing to do with a phantom field, as Meyer claims.
There's essentially an unexplained reduction of entropy and creation of new mass energy available to do work at just the right time and in just the right way.
The entropy puzzle in CCC is not solved by a phantom field, but in Stephen Hawking's discovery that black holes evaporate.
The whole point about complaining about the entropy is wrong, because the whole thing is driven by the second law of thermodynamics and the fact that black holes come about. That's where all the entropy goes into the black holes. What happens to the black holes? I mean, that's the whole story. And sure, we have an answer to that story. You may not like it, but it's nothing to do with, I don't know what they're saying. Entropy was low, sure, because all these gravitational degrees of freedom swallowed it all up.
Degrees of freedom here simply means the number of numbers you need to describe something.
All the entropy went into the gravitational degrees of freedom. They went into the black holes. These black holes finally evaporated away so late that in the crossover into the next eon, they were just tiny little pinprick. The entropy is not necessarily conserved. The degrees of freedom, if you like, are squashed out into this tiny little spot. It's not that it happens at one moment or something. Well, I mean, if it is a moment, it's the crossover moment, if you like. As one eon crosses over to the next one, that's not an ordinary size. That's a place where mass is forgotten by the universe, and you can describe it as a smooth transition, but only in a conformal geometry. There's no metric which carries you across.
This idea of kind of what happens to entropy is always an issue with cyclic models, and it seems a bit contradictory, but the way that in many of these models, including our model, it works is that it's an infinite universe. So the entropy is infinite and it remains infinite. Now, do we violate second law? I mean, if it's infinite, there's really no way to define second law for the whole universe. You could talk about the second law about in the individual patches of the universe, and that's, that is fine. But for a universe as a whole, that doesn't make sense.
One of the things he invokes is the idea that he just invokes an unexplained new concentration of mass at just the right time, activated so that the field is activated in just the right way to cause another expansion.
Doesn't make any sense to me. No, there's no new concentration of mass to do it. That's not the picture.
Now, there is an issue of how mass comes back as we move from one eon to another, but there is a proposed solution to this, which has to do with dark matter candidates called error bonds. And this is something that Meyer seems to be totally unaware of.
The general picture would be that the error bonds have gone because they decay with a half-life. I mean, some of these things need some improving in the theory, so I'll just give you the general picture. Something like 10 to the 11 years would be the half-life of an error bond. Now, I'm looking at much longer than that time, so they've pretty well all gone. The error bond masses will have gone. They're gravitons now. It'll be the universe at crossover is dominated by gravitons, gravitational radiation. No mass, fine. That's what gets through. Photons, no mass, fine. Where is the mass? Well, it shouldn't be there. Otherwise, if there was any mass, I'd be stuck. I say that there is no mass, and so the universe needs mass to know how big it is. And since it doesn't have any mass, it doesn't know how big it is. It needs a better theory than that. It needs a theory which explains in detail why this happens. I'm just giving you the overall picture, which is incomplete at the moment. I agree. It needs more calculation. It needs how to describe the error bonds properly in the theory, why they decay into gravitons, into a pair of gravitons, would be the argument, and why do those gravitons survive until the next eon, and then things are the other way around. They start to collide again and produce more error bonds. So the error bonds come back as the gravitons start to run into each other, and in the highly hot, dense new universe, it's enough gravitons running around hitting each other in a certain sense. I mean, it's hard for gravitons to hit each other, but there is an amplitude, if you like, for the graviton to make an error bond. So you will get dark matter in the early stages. This dark matter is there, it survives, slightly increases in the early stages before it gets to start to gain. It's which way around. In the early stages, the balance is to make the gravitons go to error bonds. In the late stages, the balance is for the error bonds to make gravitons. So you have to get your theory to say that properly.
To be fair, there is no theory of quantum gravity, no proposal for quantum gravity yet that kind of describes the physics perfectly or correctly near the Big Bang. So this issue is there in any approach to quantum gravity, and then this is kind of a different way of thinking about it. I'd say that the theory becomes completely scale-free. Now, I should say that there are other ideas that suggest that in quantum gravity, universe becomes scale-free. For example, in asymptotic safety, which is a different proposal. The idea is that if you go to very, very small scales, then universe becomes scale free. So that's the possibility. Now, why the mass comes back? It's a feature of the model. I mean, it's kind of doesn't make a lot of sense to say it's fine tuning, because if the model is just goes on a loop or a cycle. Now, in Roger's version, I think the idea would be that there is only one way that mass could come back. But I mean, I cannot speak too much for him. But I mean, I think that would be the idea. If the cycles are identical, then there should be only one way for mass to come back. In our version, the entire kind of universe goes in a loop. So there is really one possibility that whatever happened before should happen again and again.
And he's been critiqued by other really prominent people in the physics community.
I mean, lots of models get critiques about them. I mean, I'm glad to hear that they're taking this seriously enough to make criticisms of them, of the model.
What we point out in the Battle of the Big Bang is that every model we look at has its strengths and weaknesses, its supporters and critics, and that, of course, includes Meyer's view, which is that the universe came from nothing, or nothing physical. We dealt with that earlier on in the film, but right now, let's hear his claims about fine-tuning in CCC.
Penrose has to invoke a very finely tuned amount of mass energy that will be activated at the right time and in the right way. So there's a huge amount of unexplained fine tuning in his model. It does mean you get around the beginning because you got an infinite number of cycles, but there's no explanation for where that fine tuning came from.
I have no idea what he's talking about. There isn't any fine tuning of this sort. The main material in the universe is dark matter. And the dark matter comes about through gravitons. And it's not a question of any fine-tuning. There isn't any fine-tuning it. I don't know what he's talking about.
So I think it lacks physical plausibility in the extreme. We don't know of any other physical forces that have those attributes. The only things that have those type of attributes are agents, are minds.
The role of physics is to push, to explore the extremes, and then the way we discover new things by observing and understanding the extremes, and then we find out new things. So the things that exist in physics now didn't exist in physics 100 years ago, but we've kind of explored and tried to model things better, and now that we have other things like subatomic particle physics, neutrinos, Higgs field. All of these are things that didn't exist maybe 50 or 100 years ago. But then as we learn the universe better, then we kind of hypothesize these, and then they've been confirmed by experiments. There's just because there is something that you hypothesize that doesn't look like anything else we've seen, doesn't mean it's wrong. It just means that it needs to be explored more and either ruled out or verified.
So the final claim we're going to look at is the fine-tuning of the constant of nature. And Stephen Meyer is not alone in quoting Roger Penrose on this topic. But yet again, it's more of a misquote.
The fine-tuning of the initial conditions of the universe, what's called initial entropy fine-tuning, has been calculated by Sir Roger Penrose, the great Oxford physicist, at one chance in 10 raised to the 10th power, raised to the 123rd power.
Up so accurate as to get it to right, so 10 to the 10 to the 123. So therefore, this is sort of evidence of a designer.
Well, I used to play a joke with that by having a picture of the deity with a little pin trying to find this little point in the phase space of possible universes. And that was a joke, not to be taken seriously that somehow a creator was doing this. That was not the view I held at all. This is a joke. Okay, what do I really believe? I really believe that we need better physics to tell you what happens there. It's not chosen randomly out of the possible all the possible universes. It's just telling you that's wrong. It's the wrong picture. You have a picture which tells you it's natural the way that the universe began. And the conformal cyclic cosmology model that I have is trying to make it look natural. It's the continuation of the remote future of a previous eon. It's certainly not in the physics that we had then. You have to have an improved physics to get this to work. Sure. You need some good reason from physics why this universe happened to have all these gravitational degrees of freedom not present in the early state. So you need a theory for that. You don't need to say a creator did it, somehow got rid of all the randomness somehow by creating it for some reason to create humans or something. That doesn't make any sense to me at all.